It must be time for some AP statistics here at Fiveable. If I haven't met you yet, my name is Jerry Kossoff. If you've been here before, welcome back. If you are new, welcome. And tonight we're going to dig into some confidence intervals, specifically T intervals, to estimate either a population mean, a difference in population means, or potentially a matched pair situation. We'll talk about that at the end, kind of a special case. We'll also, we can review some Z intervals at the end if we need to with population proportions, but I'm going to spend most of the time specifically zoning in on T intervals for means. Of course, always follow us, Think Fiveable, so you can get all kinds of updates as we go. But in this stream, what I want to really focus on is reminding ourselves what confidence intervals represent. But I want to review what a confidence level is. I want to review what margin of error is, what happens to the confidence intervals when we change those parameters. And then we'll meet the T distribution if you haven't met it already, or review what it is, talk about degrees of freedom. We'll learn how to use that table in the back of your formula sheet when you're taking an AP stats test. Hopefully you've seen it before. If not, I'll expose you to what that is, and then we'll actually get into some construction. We'll do multiple choice. I've got a couple of free response questions ready to go if we need to. But we'll look at the different types of scenarios. So if you are watching on replay, be sure to use the timestamps either along the bottom or on the side. I'm not sure how Fiveable looks when you're watching replays now, but all of our replays are free and fair game for anyone to watch. So please share and spread the word that you can get some practice on confidence intervals. And at the moment, I don't see anything in the chat. A little bit of a lecture style review. We are in the part of the year where we are doing inference. And big picture wise, remember that inference has a specific goal. It is to gather information about an entire population using a sample of data or samples of data, typically just a sample of data. And the statistic you get from your sample, whether that's a p-hat or an x-bar, or a comparison of p-hats or a comparison of x-bars, will provide the basis for estimating the fact about the population, whether it's someone claims something is true, or last year 70% of people said this, let's see what it is this year, or they say the average time takes this long to do some homework task, let's see if it really does. Whatever you're trying to compare or estimate, usually we're looking for P or mu, those parameters, whether it's a categorical situation or a quantitative situation, and we're going to use p-hat or x-bar. Hopefully you know what those symbols are, because ultimately we have two big tools in inference. We have confidence intervals, which are ways of getting a range of values. So if you don't know what percentage of people are planning on doing something, okay, ask a sample, ask them who's planning to do it, who's not, and get your p-hat for yeses, and then you can use that p-hat as an estimate for P, but we then have to build a margin of error and get a range of guesses so that we can be confident that the true answer is somewhere in there. There's also hypothesis tests. That's what the rest of March will be here at Fiveable. So we're going to finish up confidence intervals today, and then the rest of the month at Fiveable will be about hypothesis tests, where we decide to either reject or not reject some kind of claim about a null hypothesis. Ultimately, when you're doing either of these, you got to make sure that you figure out what you're trying to look for, whether it's a proportion, a mean, a difference of proportions, a difference of means. Then check that the conditions to do inference are met. So we'll talk about those a little later. That's the random like the experiment is randomly designed or the sample is randomly selected, that the samples are large enough to ensure that the sampling distribution is normal, as well as there's that 10% condition that doesn't actually get checked too much, but we can discuss that. You'll take a sample, do calculations, and make some kind of conclusion or interpretation. That's the big picture. That's how I try to lead off every inference lesson here at Fiveable, with just grounding ourselves in what are we being asked to do. And now we're going to zoom into a specific feature of that, specifically looking at confidence intervals. So a confidence interval in general is taking a point estimate, taking a guess, so either a p-hat or an x-bar, from a single sample and adding or subtracting a margin of error from it. I often introduce this in my own classroom by having students guess my age, even though they don't know it. And so they come up with a point estimate to guess how old I am, and then they add or subtract a few years on either side to build out a margin of error. And then they have a confidence interval that says, you know, we believe that your age is actually somewhere between here and here. and they usually are able to capture my correct age within that. In terms of calculations, in statistics, we take a statistic from a sample and then add or subtract a margin of error, which comes from what's called a critical value times the standard error of the statistic. Critical values are either Z stars or T stars, depending on if you're working with proportions or means. Z is for proportions, T is for means. And that standard error goes back to sampling distributions, when you learned a bunch of formulas to calculate what the graph would look like based on multiple samples, p hats, x bars. And I can pull those up on a formula sheet if you need them. The confidence level, you'll hear stuff like 90% confidence, 95% confidence, 99% confidence. That refers to the percentage of the time that intervals you build in the method that you use them with a specific sample size will actually contain whatever you're looking for. So if you're doing a 95% confidence level, which is the most common one, that means that 95% of all confidence intervals you build when doing repeated samples from the same population will contain the actual parameter, the actual population mean or the actual population proportion, or in the case of my analogy with my class, my actual age. If confidence level goes up, that means that you want to become more sure that your interval will contain the correct answer. And so moving from 90 to 95 to 99% confidence means you have to cast a wider and wider and wider net to ensure that somewhere within the interval, you've contained the correct answer. So confidence level going up makes margin of error go up, which makes the interval wider. Making the interval wider means that you've got a greater range of guesses. You're more likely, quote unquote, to contain the correct answer, but your interval is less precise. So you're trading the higher confidence level for lower precision with how precise your guesses actually are. If your sample size goes up, what that does, as we saw back in sampling distributions, is as sample size goes up, the samples, x bars or p hats, should become more consistent, closer to the real population parameter. And so to maintain the same confidence level, you don't have to build as wide a net because your samples should be more consistently close to the real answer. So your margin of error will go down because the standard error of your statistic is going down. You should have seen n at the denominator of your formulas typically. And your interval will therefore get narrower or more precise. It has to do, how precise you get depends on how much you crank up the sample size. So a question that gets asked regularly every year or two in the multiple choice has to do with, what would it take for my sample? What would I have to change my sample size to make my margin of error cut in half or cut in a third or cut in a quarter? Or if I move my sample size from 100 to 400, what's going to happen? And in that case, if I go from sample size of 100 to sample size of 400, the margin of error gets cut in half. So if it was 0.06, now it would be 0.03. Or if it was 0.2, it would be 0.1. Or if it was 5 minutes, it would be 2.5 minutes now. And the reason for that half has to do with the actual formulas themselves. Both standard error formulas have a square root in the denominator with the n. And so n goes up 4 times. Well, the margin of error is impacted the square root of 4, which is 2 times. If sample size changes by a factor of 9, the margin of error changes by a factor of 3 in whatever direction. You go up by 9 for the sample size, margin of error goes down by 3 times. Down by 9 times, margin of error will go up by 3 times. So it's whatever the trade-off is there. It's a square root of whatever factor you're changing by. As a visual for this, for everything that's on this slide, we're gonna switch screens here and trade over to this guy. On this screen, what you're gonna see is we're gonna estimate mu. It's a population mean. You see the green bar represents where the population mean is. There's no numbers there because we don't actually know what it is. We just know that it is something. And when I take samples, I'll do samples of size 25 from this population. Okay. All the yellow dots represent the individuals in the single sample, and the dot in the center represents the X bar. Notice that I've taken a few samples so far, and I've gotten a bunch of different X bars. But when I build out a margin of error on either side of the X bar, somewhere within that interval has contained the correct answer. And with my confidence level being 95%, what that means is if I keep this process going, taking more and more and more samples, I should have a hit rate or a capture rate of about 95% in the long run. So I've done 140 samples so far. 94% of them have contained the correct answer at some point. Now it's 95. I'm hovering at 95. I was waiting to get one where you could see that sometimes even with the margin of error, your X bar was so far away from where the actual population mean was that you end up missing the correct population mean. So just because you build a confidence interval doesn't mean the actual population parameter is within it. There's always a case where we might pull an outlier as a sample and end up far enough away from the real answer that it just doesn't work. But if I increase this confidence level from 95 up to say 99, what you'll see is the confidence intervals themselves got a lot wider. And you'll notice that more of the confidence intervals now contain the correct answer because I cast a wider net. I used a bigger critical value, Z star or T star. In this case, it would be, well, we'll see in a little bit which one it is. But if I decrease the confidence levels, the intervals get narrower. And now more of them are shaded red for having missed the population mean. In my 240 trials now, only 91% have hit it at my 90% confidence level. I keep this sampling process going. That should level out to 90% here. It should level out to 95% at a 95% confidence level, and it should level out to about 99% at a 99% confidence level. So hopefully we see what we saw on the last slide, which is confidence level goes up, margin of error increases, more of the confidence intervals contain the correct answer, and I should be more confident that my specific interval that I get from my specific sample will contain the correct answer. If I go ahead and change the sample size, what's going to start happening is you'll notice the margin of error is getting much smaller. The reason for that is every X bar on average is now closer to the actual population parameter, as mentioned before. The sampling distribution gets more consistent because even with a couple of outliers from the far end of the population, with 50 individuals to balance it all out, the X bar doesn't get pulled as much by those outliers as it does if I only had a sample of 25 people or even 10 people. And if I keep sampling a bunch, I will have some confidence intervals that miss the boat. I had 2 in a row there on the middle of your screen. But so far in 113 samples, 108 or 96% of them have contained the correct answer at my 95% confidence level. So when I say capture rate, confidence level is what percent of all confidence intervals that you would make from a repeated sampling will result in an interval that contains the correct parameter somewhere within it. That's what confidence level is. So on a multiple choice situation, if you're asked to interpret confidence level, you're looking for the one that mentions that percentage of intervals containing whatever the parameter is. They'll try to make it into a probability thing of like each interval has this percent chance of containing it, but it's not about each individual interval. It's about a repeated sampling process and over the long run, what percentage of your intervals will contain it. Because each interval either does or doesn't contain the correct answer. There's no probability involved. It is 95% of my intervals in the long run will contain the correct population parameter. And so that's a brief review of what confidence intervals actually are. We're going to switch back over and now go ahead and discuss some specifics of like actual T intervals. So we're going to go ahead and meet what I mean by T, what the heck T is referring to. When you first learned about normal distributions, you probably learned about z-scores, meaning like the number of standard deviations away from the mean that you are in a distribution. And that required us to know the population mean and the population standard deviation. When we're doing inference, we probably don't know what's going on about the population because we're trying to estimate it. That's why we're doing the estimation in the first place. And so what ends up happening with that is instead of knowing the population standard deviation, we have to estimate it from a sample. But if I take just a sample of data, the sample mean and the sample standard deviation might not match the population mean and the population standard deviation. And the smaller my samples, the more variance I have in the different results. And so my sample S's, or sample standard deviations, might not actually be good estimates for the overall population standard deviation. And so there's another thing called a t-distribution. So a standard normal distribution is sometimes called a z-distribution. You got your z-scores. The mean is in the middle, standardized at mean is 0, and you count one deviation up and down 3 times, and you get the nice bell curve shape. T-distributions also have a bell curve shape, but they have less data in the middle and more data out on the edges from the increased variance of sampling versus dealing with an entire population. And what you see on the screen is 3 drawings. So the drawing with the biggest peak in the middle is your Z distribution, the typical standard normal distribution. And the other 2 drawings are T distributions with degrees of freedom 5 and degrees of freedom 2. So smaller samples. Degrees of freedom is a concept that has to do with how big your sample is. Degrees of freedom is always 1 less than the sample size. That's a thing that you should memorize. But I have a lot of students often ask me, like, what the heck do you mean by degrees of freedom? I don't know what you're talking about. And it's kind of hard to explain in a statistical context. So there's a lot of good analogies we can use. So let's take, for example, a 7-day week. And there's an analogy I'm going to use here. So let's say you are the kind of person that wants to wear a different hat every day of the week, and you have 7 different hats, 1 to wear on each day of the week. On the first day of the week, you have 7 hats to choose from. Put on your hat, go to school, go to work, go wherever you're going to go, and you're good. Now, the next day, with 6 days left in the week, you only have 6 hats remaining. And since you've already worn one and you don't want to wear it twice, you have 6. You're free to choose 6 of your hats. And the pattern continues where the next day you're free to choose 5 of your hats. The next day you're free to choose 4 of your hats until you get to the second to last day when you have 2 hats left. Now, whichever hat you pick, you are locked into the other hat for the last day. So for the first 6 days of the week, you got to pick whichever hat you wanted, but the last day, you're locked into whatever the final hat left over is. And if you think of other scenarios like this, where it's like, hey, you've got to pick, there's 5 things on a tray and you've got to give them out to 5 different people. As soon as you've given out 4 of them, the last 5th thing is automatically going to the last person left. That last person in line isn't free to choose whichever one they want. So if there's like 5 different flavors of cake on a plate and 5 people in line, the first 4 people will get a choice. They'll get some degree of freedom, but the last person does not have choice. So you're locked in. So there's always 1 fewer degree of freedom than there are individuals in your sample. From a mathematical context, it has to do with the fact that we are calculating X bar. And the way to calculate X bar is to add up all the numbers you have and divide by the number of numbers. Well, if you have a sample size of 10, as soon as you've added up 9 of your numbers, the 10th number has to be locked into place to create your X bar. And the first 9 numbers could be anything. You could make up any 9 numbers in the world, and as long as you know what the X bar is supposed to be, you could always solve for that missing 10th number. And so the 10th number would get locked into place. And so degrees of freedom, always 1 less than the sample size. What happens with a t-distribution is as degrees of freedom go up, as the sample size gets bigger, the amount of variation will decrease slowly, just like any other sampling situation. And as the amount of variation decreases, the area in the tails starts to get smaller and smaller and push more towards a regular Z shape. And so degrees of freedom higher makes your T's closer to your Z's. And the way we can see that in a table on the AP Stats exam is with table B. This is critical values for a t-distribution. Was not able to put the whole page on here because it was just too much to fit. But what you should see at the bottom, you should notice different confidence levels. And hopefully you recognize the bottom row right above 95%, 96%, 98%. You should recognize some Z stars like 1.96, 1.645, 2.576, some common numbers you used when you were estimating population proportions and building Z intervals. Well, those are on the bottom row of table B. The rest of the table contains T stars, or critical values for the T distribution. And on the left-hand column, you'll find the degrees of freedom. And then you line it up with whatever confidence level you want. And whatever's in there will be your T star for your confidence interval. So anytime you're doing a confidence interval to estimate a mean or a difference of means, and you have to write out what the interval is and what the T star and the standard error and all that stuff, this is where you find the T star at. So remember to always use a degree of freedom one less than your sample size when picking out a T star. The bottom row has all your Z stars. So in case you didn't memorize 95% is 1.96 or 70% or 92% or any of the weird percentages, they're all along the bottom there, and you are good to go with Z stars. Okay. So we've reminded ourselves what confidence intervals are and what happens to our intervals when confidence level and margin of error change. We've met a T distribution. Ultimately, the thing you need to know from it is if you're doing an interval to estimate a mean, you will be using a T distribution or a T interval or a T test. And if you're doing something for proportions, you're doing a Z interval or a Z test. So 99% of the time, Z is for proportions and T is for means. Z proportions, T means. So now let's get into it. We know that confidence intervals are built by taking a statistic from a sample and then adding or subtracting a margin of error. The margin of error breaks down into a critical value and the standard error of a statistic. With Z intervals, the statistic was p hat, the critical value was Z star, and the standard error had to do the square root p hat, q hat, or p hat 1 minus p hat over n. For T intervals, the statistic, we're trying to estimate the population mean, so we'll take a sample mean, that's an X bar. The critical value will be a T star based on certain degrees of freedom, and the standard error comes from the standard deviation of the sample divided by the square root of the sample size. This S over square root of n, you should recognize from previous units with sampling distributions. The T stars we just met, and X bars are just sample means. So here's an example multiple choice question. Biologists studying a certain bacteria want to estimate the mean lifespan of a single bacterium. In a large petri dish, the biologist observed a randomly selected group of 9 bacteria. The mean lifespan of the 9 bacteria was 4.3 days, with a standard deviation of 1.5 days. Assuming all conditions for inference are met, which of the following is a 95% confidence interval for the population mean lifespan of a single bacterium of this type? They say 95% confidence, so we know our T star has to come from the 95% column. I say T star instead of Z star because we're talking about mean. They're trying to estimate mu. We have a randomly selected group of 9 bacteria, so our sample size is 9, n is 9, which means the degrees of freedom we need to use is 8. So before I reveal the answer choices, let's look back at this T distribution. I got 95% for my confidence level, but because I'm estimating mean, I need to be using the T stars instead of Z stars. So if any answer ends up having 1.96 with it, it's not right for this situation because 1.96 is a Z star, not a T star. I'll then look at the 95% column and notice that at where DF is 9, it's 2.262. But DF stands for degrees of freedom. Degrees of freedom is always 1 less than sample size. Since my sample size was 9, I really need to use DF as 8. And where DF is 8 and I line up with 95%, I see 2.306. 2.306. That's my T star. And now when I look at my answer choices, I can eliminate A and B because they've got 1.96 for the Z star instead of the T star. So I'm between B and D. Now B and D both have 4.3 in the same place and 1.5 in the same place. That's sample mean and sample standard deviation. They both got the same T star. They've got different denominators. B has 9 and D has 3. And if you look carefully at the standard error formula, you'll notice square root of n is the standard error of statistic, and n is the sample size. Square root of n has to go down there. So it's not 9, it's the square root of 9, which hopefully we know our basic algebra, know that the square root of 9 is in fact 3. So in a multiple choice setting where they often ask us to build confidence intervals by plugging stuff into the appropriate formula, but not doing anything else, that is my answer. If I was doing this in a free response setting, I would have access to my calculator, which I could just type this sample data in and just have the confidence interval spit out for me. If I'm doing a t interval, on my TI-84, I go to stat, tests, and I slide down until number 8 where it says t interval. So you'll see a bunch of tests at the top. T interval is number 8. I usually input stats. There's a choice between inputting data or inputting stats. Data is when you have to input a whole list of individual values. The AP exam has gotten away from giving just basic lists of tables without a summary statistic at the bottom. So even if you had all 9 bacteria's data, they would still put X bar is 4.3 and S is 1.5 at the bottom of that to save some time. And so then I see on my screen, I see a space for X bar, I see a space for S, 4.3. My S is 1.5. My N is 9. My confidence level is 95%. And then I let it calculate, and it will actually turn what's choice D into an interval going from the lower boundary to the upper boundary. Mine says 3.14 to 5.45, which if I then actually multiply out 2.306 times that and do 4.3 plus that, yeah, I'm getting the same answers from simplifying choice D as I did from my calculator when I went to stat, test, t interval, and input the statistics, not the data. So in a multiple choice setting, because they know you can just punch it in your calculator, they're mostly testing your ability to set up the situation using the formula sheet. But in a free response setting, of course, they know you're going to use your calculator. So they're not actually really testing the setup as much as they are the whole process. And the whole process for constructing and interpreting a confidence interval for proportion or mean or parameter or whatever we're doing, you have to first check conditions before you go to the calculator and type stuff in. 2 things you've always got to check. The sample was random or the experiments were randomly assigned, and the sample is large enough. For proportions, the magic number was 10. For means, the magic number is bigger than 10. It's 30. It is 30. If your sample is less than 30, we can still potentially do a confidence interval. We just have to ensure that the given data we're looking at is not highly skewed to the point where I would assume that the original population is skewed. Because if the original population is skewed and the samples are less than 30, that's not enough for the central limit theorem to guarantee that the sampling distribution of X bar will be normal. So if my samples are small, but my sample data looks like it's fairly symmetric, then it's reasonable to assume that the population is normal and my condition is met even without a large sample. So be on the lookout for sample size. If the sample size is small, they're going to give you a graph to look at. Be on the lookout for that graph being fairly symmetric with no clear outliers. And as long as that's there, then you can say, even though sample size less than 30, the original population appears to be normal because the sample data appears to be normal. Check. Once you've done that, you need Okay, we are back. Apologies for that. If you're watching on replay, hopefully I cropped it out. I might not have. But we were just discussing the end of how to do free response. Oh, no, close video. I want to bring it up. Okay, we're back. Okay, there is someone here in the chat. I've been talking a lot at the screen. I haven't known if you've been there. Before I like kind of go to the other parts, I'm curious how you feeling right now. Has this felt beneficial? Do you got lingering questions? I tried to do a couple examples and show some things. Maybe you're just soaking it up. Anyone home? It's all new to me. Okay, cool. This was all new. Have you done any confidence intervals yet? Or have you been on like sampling distributions where you're taking samples and making X bars and P hats? Or was this all like totally brand spanking? I never heard any of this before. Because I can recognize this would be a pretty overwhelming if it was brand new. The streams are meant to be a little like, it's hard to strike a balance between like reviewing content that people know and doing an intro of something for people who don't know, because you gotta try to strike the balance. Okay, still doing z-scores and normal distributions along with empirical rules. All right, so that's a little bit back, I will admit. That depends on, you're probably doing probability rules with that, so that you're not maybe too far back. But when you do get to this, it does mean that your teacher is going to have to kind of cut some corners in certain places. In terms of like the actual what a confidence interval represents, where we're trying to figure out something about a population using a sample, that's like the biggest picture of what inference is. It's taking samples of data and using the results of the sample to make predictions about the entire population. I also recognize there are a lot of symbols in this part of the course that can be, tricky and stuff. So if I've been saying population mean, like mu and sigma, if you're doing z-scores and stuff, you should be clear with those. If the numbers are representing a sample, so instead of like, the average for all kids at the school is this, it's an average of the sample, that symbol will be an X bar. And the standard deviation of that sample will be an S. And the N stands for how many people are in the sample. And those numbers combined, when you just put it together with a little formula and attach the degrees of freedom to it, will give you your confidence interval, which you can then say, all right, I am pretty sure that the actual population mean is between here and here. When you're doing empirical rule stuff, you're saying that you already know what the population mean and standard deviation are. And if you're normally distributed, you'll have this percentage of the population within certain boundaries. We're using that fact to come up with those critical values, where the Z stars are like 1.96 because they say 2 deviations should give you 95% of the population with the empirical rules. Well, it's technically not 2, it's actually 1.96 deviations. So based on taking samples, 95% of all sample means or sample proportions should be within 1.96 deviations or standard errors of the overall population parameter, P or mu. And so what you're doing with z-scores and normal distributions is the basis for all these inference things. So hopefully that helps a little bit. So we've done a couple examples of a multiple choice scenario, discussed what you need to do for free response when it comes to that. And the thing that's different with means when it comes to intervals is a lot of times what we're trying to do is compare different groups to each other. So if you have 2 data sets, you might want to figure out, is there a difference between these 2 data sets? So it could be a treatment group versus a control group. You know, with plant growth or something, you could give a certain group fertilizer and not give a certain group fertilizer and see the difference in the weights of the plants that grow. You could do a before versus after kind of situation. A lot of like medical trials will do this. Like you measure something before you start taking the medicine and after you start taking the medicine. Or in schools, like pre-test, post-test. Got to measure how people do before, how people do after. Two different classes, compare this class versus that class, or compare men versus women, or compare high schoolers versus elementary schoolers. Ultimately, you're then, instead of trying to estimate each individual mean, you're trying to estimate what's going to be the difference in the means of the two groups. But sometimes the data comes from two separate samples, and sometimes the data comes from the same sample. So if you've got like class A versus class B, there are different kids in those two classes. Those are two independent samples. But if you're doing a before and after test with the same people doing the before and after test, the before data and the after data aren't independent of each other because it's the same people. And so if you have independent samples, instead of doing a regular t-test, you'll have to do a two-sample or regular t-interval. You have to do a two-sample t-interval. But if the two sets of data come from the same group of people, like a before and after, or everybody tries keyboard A and then everybody tries keyboard B, and we compare how fast you could type on the two different brands of keyboards, that's called a matched pairs experiment. And so you will do a matched pairs interval. And instead of putting in the two separate sets of data, where you put in two separate X bars and two separate S's, like you do with independent samples, you would put in just the single X bar and S from the difference in before and after, or from the difference in A versus B. And what the AP exam will do is they'll list the results from each group of each part of the experiment and the differences. And so if you are doing a matched pairs test, you'll use a one sample t interval with the difference of data. And in a future week, I realize I don't have a problem on deck ready for that. When we're doing some more inference review, I'll make sure we have that. But ultimately, there are 4 types of intervals you would be asked to build on an AP exam. All of them on your calculator can be found on the stat test menu. Scroll past the tests and go into number 7 through 0, I think, all the intervals. You've got Z interval, T interval, 2 samp Z interval, 2 samp T interval, 1 prop Z interval, and 2 prop Z interval. Okay, 1 sample Z interval for a population proportion is when you're trying to figure out what percentage of the population do something from a single sample. And that is letter A on my TI-84, 1 prop Z int is where I get that. Means of 2 data sets we use experience. Sometimes comparing 2 data sets comes from an experiment. So you could still compare means of 2 data sets from separate random samples from the separate groups. But in an experiment, if treatments get randomly assigned to different individuals, and you have treatment A versus treatment B, and now those are 2 separate groups of people from random assignment, now you can compare the 2 groups. And since it was randomly assigned, you could also do a 2 sample interval to compare the difference. We could also do 2 separate random samples for an observational study and compare in that way. So some of the situations will be described as 50 people were randomly selected and asked this thing, and other situations will be 50 people were randomly assigned this placebo or this treatment or whatever the situation is. 1 sample T interval is for population means, or when you're doing a matched pair situation. So that would be specifically in an experiment where both groups of data were the same people each time, before versus after. One of the scenarios on an AP exam a couple years ago was like they recruited 15 soccer players and made all of the soccer players kick 1 ball filled with air and 1 ball filled with a different gas, and compared how different their kick lengths were. And since everyone was doing both things, that's a situation where the 2 separate data sets aren't really separate. They're attached to the same people. But if you're doing 2 sample intervals, they have to be very clearly from 2 separate independent groups. So either in an experiment situation, people were assigned to separate treatments without ever overlapping, or you did 2 separate independent samples from 2 groups of a population. So if a large company wants to know if men and women have different satisfaction levels about something, if they get a random sample of 50 men and a random sample of 50 women, that would be a 2 sample interval, depending on if it's proportions or means. So if it's what percentage of you say you're satisfied, Z interval. What's your average score on a survey? That would be a 2 sample T interval because you're measuring means. But that's for separate independent samples. And then the 1 sample data is for single groups of people. Even if they're doing 2 separate things, you can make a match pairs and do a t-test. So with that, we have reviewed what confidence intervals are and how margin of error and confidence level impact the appropriateness of the confidence intervals and how well they work. We've learned what degrees of freedom mean, that they're always 1 less than sample size. And we have actually looked at a couple examples of making T intervals. Last week, we did some Z intervals. And the next few weeks here at 5 will be all about hypothesis tests. And by the time we hit the end of March, we'll be reviewing all of this big picture inference stuff with hypothesis tests and confidence intervals. And so if you're watching on replay, this is where the new material for this will end. If you are still here with me live, I'm happy to take some more open questions. I can try to go backwards if I need to. I can try to go forwards. No question is too basic or too advanced because I am here for you and for your service. So I think Lafuz is with me right now. If you got some questions, lay them on me. If you're like feeling good, then we'll wrap it up. Yeah, absolutely. I would imagine I would have questions too if I had never seen confidence intervals before coming to this. So again, if you're watching on a replay, new content is done. I'm going to answer some open questions now. If any specific topics came up, I'll put them on the side where the timestamps are. Otherwise, I'm just going to be here for another about 10 minutes or so, answering some questions. If you can see my screen, I've got some paper that I can write things on if we need to, or draw some stuff. Or I could also use the, the PowerPoint. Do you think I need to learn to catch up on? Yeah. So different classes go in different orders. So I do need to make sure that I gotta get a sense of what you've done. Have you guys done, so if you're doing normal distribution, that means you've probably done basic data analysis. You've done describing histograms and finding mean and median and range and standard deviation and stem plots and box plots. Okay, have you done regression and scatter plots, two variable data sets? So residuals, predictions for explanatory response variables, predicting the response variable from the explanatory variable, learning about correlation coefficients and is the association positive or negative, weak or strong, linear or nonlinear. We've done 2 variables. So you've done the 1 variable data analysis. What about the 2 variable data analysis? Ooh, okay. So that is called linear regression. I'm gonna see if I can actually pull these up while we're talking. I did a series of streams back in the fall on linear regression, and I'm going to see if I can pull up at the minimum, I should be able to pull up the slideshows for those, and I'll put them in the chat. But when you go into Fiveville, you should be able to see the replays of it. Full disclosure, it was in 3 parts, and I don't think anyone showed up to any of the 3 parts, so it was just me talking at a blank screen. So let me find these notes. So scatter, all right. Okay, is it gonna work? Okay. Okay, so that should lead you to an intro PowerPoint about describing scatter plots and distributions and looking at things. And then you should be able to find, I think it's called like describing bivariate data part 1, something like that. And then where's part 2? Using regression line. This was part 2. You got an error? Okay. Let me see. Oh, yep, you did get an error. I got one too. All right, let me try again. No, it's link in view. Try that. It just worked for me, but it also might have worked for me because it was my presentation. All right, cool. So that's part A. And then I'm also going to drop in there part B. That should also work. Okay. You'll be able to find videos that go with that. And regression is usually like, of the 6 free response questions, one of them is usually about these topics. So describing the association, calculating residuals, or making predictions with regression lines. So those 2 would be good to brush up on even on your own. Have you guys been doing probability rules at all? Or like calculations with probability? Okay. Are you in a 1 semester class or a 2 semester class? Like, did you 1 semester? Oh, okay. Yep, that'll do it. Because a lot of like, that probably has actually a big part to do with it. So yeah, I'm wondering how you're actually gonna get to all of it. I'm guessing you probably then see your class every day and have pretty long classes. So it's distinctly possible that through the month of March and April, you'll like get to a lot of stuff. But this is typically taught as a full year course because there's a good chunk of stuff to get to. And so it's likely that you have some things coming up. Have you done, when I say like experiment, observational study, survey, different sampling methods, have you all touched that yet? Okay, cool. So then probably what's going to come, actually my guess is then, I actually think the stuff I just sent you is probably what's coming up next for y'all. After the normal distribution, a lot of people go right into regression and to scatter plots and stuff. So you might get a good preview of some of your classwork there. The other thing that might come after that would be just other probability rules. And if that's the case, we did some review here in January about that. So you'll be able to find in the 5 lat. So that should give you some good stuff to look over, at least just some like basic PowerPoint slides, and then you can find accompanying videos to go with them. And don't just restrict yourself to 5able. Usually, I don't know if, I think Khan Academy has statistics videos as well. But there are other places you can definitely find some stuff. The College Board website will tell you like what the standards are, at least, or like what the units are called and stuff, so you can figure out what you have and haven't done. And that can give you a place to start looking ahead and making some self-study plans. Because what inference is about, confidence intervals and hypothesis tests, builds off of all the previous units. So like one of the conditions is you have to have a random sample. So we got to know how to do random samples. And all the symbols show up throughout the first semester in different contexts. So you know how to find mean and median and all that stuff. Well, if it's from a sample, it's one way. If it's from a population, it's another way. And if we don't know stuff about the population, we use the sample to figure stuff out, but it's based on probability rules and things you'll learn with sampling distributions, which will come after you do all the descriptive statistics. So hopefully your class pace picks up a little bit, and by the end of March, you'll be, on board with where we're at mostly at this point. But we are heading up towards 9 o'clock. I have time to answer maybe 1 or 2 more questions. If you have anything specific about the content you're currently working on, I'd be happy to answer something, or anything else. Yeah, comparing means. Yeah, so let me go back to this situation. So this sample problem we saw was about, we wanted to find a 95% confidence interval for the mean lifespan of one type of bacteria. What we could have potentially done instead is maybe the biologists wanted to see if there's a difference between the lifespan of this bacteria species and a different bacteria species. Or maybe the bacteria as it shows up in North America versus the bacteria as it shows up in South America. And so in those cases, instead of trying to just figure out what's the population mean for this one group, I'm trying to compare the population means of 2 different groups. My school district has multiple high schools, and we have comparison data of like, all right, the average SAT score at this school is 1,000, and the average SAT score at this school is 1,100. And so you could compare, the different scores to each other usually through subtraction. So instead of trying to just estimate mu, we're trying to estimate the difference between mu1 and mu2, or mu A and mu B, or the mu for men and the mu for women, or the mu for North America versus the mu from South America. So there will be subtraction involved. You're not going to end up making a range, but what will happen is, let's say, I'm trying to think of a good relevant example here. So let's say I'm going to take 10 kids from a class, and I'm going to give them a pre-test and a post-test. So I want to see how much they grow over that year. And the first kid on the pre-test gets a 70, and on the post-test gets a 75. So for that kid, the difference in their score is +5, because I subtracted the end from the beginning, or beginning from the end. The next kid, pre-test 50, post-test 70. The difference for that person is 20. The third kid, pre-test 80, post-test 78. Uh-oh, they're at a -2 because they actually went down to the post-test. And I would keep that pattern going of looking at the before and the after and subtracting the difference. But then I would have 10 new numbers. I would have the +5, the +20, the -2, and all of the other differences. Then those 10 differences become my sample, and I'm looking at what the average difference is between the two samples. So in the matched pair situation, like a before and after with the same people, you're estimating what the difference for each person was by looking at the literal differences between before and after. If you're going with two separate independent samples, you find the sample average for the first group, the sample average for the second group, and then literally subtract the averages. And it comes up with an estimate for the difference in the population means. So there is subtraction involved, but it's on an individual level, or if it's independent samples, you subtract the final results from each other and then use that. Okay. And so in context, it will come up a lot of times in a situation with an experiment, because in an experiment, you explicitly are trying to compare two different groups, a treatment group and a control group, or version A and version B. And some special experiments, like you might have learned about matched pairs experiments, use each individual as their own control group or as someone who does both treatments. And in that case, you would do a one sample interval or test because it was only one sample of individuals doing both things. In the case where people are separately assigned to different treatment groups or separately selected from different populations, that's when I do the two sample procedure to estimate the difference in means. Thank you for asking that question. And with that, we reached 9 o'clock. Thank you for coming and stopping by. Hope to see many of you watching out here again next week. Thank you.